We're going to build a solar water splitter that's wireless, just like a leaf. You can think of it as an artificial leaf. It's going to have a cheap metal oxide photoanode that absorbs blue light, a cheap silicon photocathode that absorbs red light, a membrane, a polymer membrane separator, and catalyst, cheap catalyst to oxidize water, and a cheap catalyst to reduce protons to hydrogen. No platinum, no expensive metals. Everything's going to be cheap. Right now, this photoanode's tungsten oxide, which we've doped. Right now, this photocathode is silicon, cheap. And our catalysts are cheap, as I will show you. Next slide. If you start thinking about what you want to use for catalysts, if you want to use earth-abundant materials, you first start with nature. How did nature evolve hydrogen? Nature did it with enzymes called hydrogenases. And they have these complicated protein structures. But their active sites have irons and sulfurs in them that look like this in these structures. But if you put these on our photocathode to evolve hydrogen, they don't last very long. They're proteins and they're very fragile. And they irradiate away in a few seconds. They're gone. We can't use them. Then you could say, well, take the heart, the catalytic heart out, and lots of people make these things. They're called bioinorganic chemists who work in this field. They build the active sites of these big enzymes. But we've learned one thing in 30 years of bioinorganic chemistry. When you take the active sites out of the protein environment, they don't work anymore. They don't work anymore. There's a reason proteins are big with lots of interactions. They make things function. When Marcetta Darensberg at Texas A&M and Tom Rauchfuss at the University of Illinois have done some beautiful chemistry, making these mimics of the active sites of hydrogenases. They work, but at extremely negative potentials, way out of the range we could ever reach with sunlight. We can't use them. We did a worldwide search for catalysts, and we found that cobalt is the answer. Next slide. These cobalt compounds, so-called glyoxime compounds, are terrific catalysts for hydrogen evolution. We can make electrodes out of them. Next slide. We have found that we have worked for years to understand what the mechanisms are, and we found that they go through something called a cobalt-3 hydride. And work by Gillian Dempsey in my group, who Suze knows very well, has worked out all of these mechanisms. This cobalt hydride can react with itself to eliminate hydrogen, or it can pick up another electron to make an extremely reactive cobalt-2 hydride, which reacts with a proton directly to make hydrogen. We have worked, Gillian in her work with me as a student has worked out all of these mechanisms. And now we're putting them on silicon, on the photocathodes. Next slide. We're putting them on right in here on these photocathodes, these cobalt systems. And a number of people in my group, Judy Latimer, Mike Rose, Leslie O'Leary, and Nate Lewis's group, all working together. We're making these working photocathodes out of these cobalt systems. So we do have a cheap version of a hydrogen evolving system. We also have heterogeneous catalysts made out of nickel and molybdenum, so-called NEMO, N-I-M-O, NEMO. We have found NEMO. And NEMO on this works great too, and there are 2 or 3 others. Bottom line is, we've got this hydrogen evolving problem now under control. We've got working photocathodes that are microwires of silicon, very good absorbers of sunlight, and we've got the hydrogen evolution working without platinum. We have got it working without platinum, just as well as it was working with platinum. So we have taken that step. Now what's left? What's left is the huge problem. How are we going to get the electrons from water? We can't afford to get them from natural gas, which is where you get hydrogen now that's being used. We got to get it from water. In order to get it from water, we have to oxidize water. Lisa, next slide. The challenge is what we call water oxidation here. We have got to get cheap water oxidation catalysts. And the next slide, here's the state of the art as of 2008. this inorganic special issue of Inorganic Chemistry, which Rich Eisenberg and I edited March 17th, 2008. We actually reviewed all of the catalysts around that could oxidize water. None of them's very good. None of them is anywhere near as good as the natural one, this manganese one in photosynthesis. But you can look at this. Since that time, there have been a large number of great developments. Next slide. There's been this manganese system that's made by Dismukes, who was at Princeton and is now at Rutgers. That's a good looking one. There's one at Emory. Emory has one that's great. It's this cobalt chain here in this phosphotungstate. This one looks very, very good. Craig Hill is this is an undergraduate, by the way, who made it at Emory. An undergraduate made this catalyst. His name is Ben Yin. It's Q. I can't pronounce any Chinese word that starts with Q. But we call him Ben. Ben made this, and Craig Hill, of course, took the credit. As is usually the case, the professors will always take the credit. You know, that's the way it goes. But these are both very promising catalysts that have just come out in the last year or two. And then there's the famous MIT catalyst by Dan Nocera. Next slide. Nocera's group, Yogi, this guy Yogi, who's an unpronounceable last name, so we call him Yogi, made this cobalt system that we think has this structure and goes through some funny oxidation state. This looks like a really great catalyst, this one from MIT. So now we've got 2 cobalt catalysts that are working and 1 manganese one, but none of these still is nearly as good as the natural manganese one in photosynthesis. So that's when I formed the SolarArmy. Decided to get all the kids in the world working for me on this, all the kids. I said, come on in, kids, join the Army. We're going to do something great. We're going to find the best catalyst in the world to split water, to oxidize water. We're going to have a worldwide solar material search. Next slide. We're going to start with a periodic table. There it is, in all its glory. There's a sort of version of it here. It's sort of wrinkled. If I may say so, you have one of the most beautiful buildings I have ever seen in chemistry and one of the worst periodic tables. Get a periodic table you can be proud of. And this wonderful facility and this wonderful campus you have with such great students and such professors. So we start here, and now Lisa hit the button, and we're going to search in here. We decided we would search in this region of elements that we thought would make metal oxides. Now you see what we're doing is we're going to search for a whole combination of metals. We believe out there somewhere, undiscovered, yet undiscovered, is a catalyst, is a metal oxide catalyst that's as good or better than the one nature finally ended up with. This is the worldwide search. But now, unfortunately, next slide, we have to cross out all the ones that we know work and are expensive. Platinum, iridium, ruthenium. These are all the expensive metals. Gold, all the nice ones. We're not allowed to use those. We can't scale them up. We got to search here. And of course, next slide, we're going to make oxides. We're going to combine with oxygen and make all the combinations known to man of all of these systems, and we're going to test them and find somewhere there's going to be the fantastic catalyst we're looking for. Next slide. They're going to be robust. They're going to be like rocks because they're metal oxides, and metal oxides are rocks. They're rocks all over the planet. We're going to make a catalytic rock. It's going to last forever. And if you think if we're going to use 3 metals at a time, there's going to be millions of combinations. If we 4 or 5, there's going to be billions. Next slide. Millions. So, got to form the SolarArmy. Next slide. There I am. I want you. My students photoshopped me in. There's your hero there. I want you for the SolarArmy. Suze knows this. Here's the way it goes. Starts with the U.S. government. That's, of course, the downside. It's a cross we bear. Fortunately, I fund the National Science Foundation, the DOE. The National Science Foundation funds our program, which is called CCI Solar. If you want to learn more about this, you can Google CCI Solar. We got a lot of cool stuff on this website. You're going to see some of it here. I got 17 university research groups, and I got hundreds of kids worldwide at undergraduate colleges like this one and high schools. Sue's helped me move it into high schools. We're now in 15 high schools. We got kids in after-school programs searching for solar materials. I got kids in colleges all over this country, all over the world actually, in this search in the SolarArmy. Next slide. Here they are. We call them the School of Sharks. We've got a whole bunch in Southern California. By the way, Sue's report is we're now in like 15 high schools now in Southern California. You were at Poly. We're now in PHS. We're in Muir. We're in a whole bunch, San Marino. We're all over the place now with kids, with mentors. We're all over the place here in 2 sites in Germany. What do we do? Here's what we did. We figured out how to hack an inkjet printer and fool it so it thinks it's printing ink, but it's really printing chemicals on conducting glass. Next slide. Prints them in these arrays. So we started with an HP printer. We're now using other printers because the HP is no good. And they didn't cooperate with us. And so we've dumped them. We're into other better printers now, but we started with an HP. We put a conducting glass here. We hack the software. And so we make it print metal nitrates on conducting glass. We then stick those first on a hot plate, then we fuse them in an oven. We heat them up to 500 and 600 degrees to calcine them to make a amorphous level of metal oxide catalyst on the film on conducting glass. We rig it into a electrochemical system with a Lego set that's called the Lego Mindstorm Scanner. Next slide. There's our Lego set. You can get Lego Mindstorm Scanner. We've rigged it so we put next slide, we put a green laser pointer in it, and it scans our potential catalyst here, and we record the photochemical, electrochemical activity, and we get a big voltage and current hit. We know it's splitting water. We know we've got a hit. We know we've got a catalyst. And those kids are doing that in high schools after school, and they're doing it in colleges. And Sue's, one of our leaders, is right back here. She's now in Charlottesville. She drove over here. She knows. She's done this herself. She's right in the audience. And we got software to convert these hits with software into big bright spots. By rigging the software, of course, we can make false images. And if we get a big hit, we get a big bright spot. And the kids know they got a hit. They put it on the web. We got a huge website. We're like David Letterman. We got the 10 biggest hits on our website from all over the world. When these hits come in, we have no idea what these things are. We know that there's some iron in them and something else in them. Every time a kid gets a hit, we got a huge research problem at Caltech to figure out what these materials are. What are they? Where's the iron? Where's the other stuff? What's the structure? How come it's a big hit? And the biggest hit we got so far is at a little college, next slide, in Iowa. Our Grinnell College site, a little gal by the name of Stephanie Chung. Right there. Notice she's not in the picture. The professors take their pictures. It's another disaster. Brad, it's a disaster. You know, Bill, the professor's taking all the credit. So I met with Stephanie. I said, Stephanie, what's the real scoop on this? She says, Harry, let me tell you how to make these. These guys don't know how to make them, but I do. And Stephanie told me how. It's zinc, yttrium, and iron. Huge hit. Zinc, yttrium, and iron. A huge hit. Nobody ever thought of that. She was out there. She threw some yttrium in. Why she did that, nobody knows. But she liked yttrium. I guess she likes a Y or something. And so there it is. This is a huge hit. When a hit comes in, you see, to Caltech, as Suze knows, we don't really know what it is. We can't now the job is, can we reproduce it? Can we figure out what this hit is? It's just a discovery out there with our Lego set and our inkjet printers and stuff. It's come in from Grinnell College. So here's what happens now. I put my SolarArmy on it. I put a bunch of students, high school students, undergrad students. I put your students from Poly on it last summer, all summer. You know, Claire, John, the whole schmear, and the kids from Caltech on it, and the postdocs. I got high school students, undergrad students, grad students, and postdocs, all trying to figure out what Stephanie Chung discovered at Grinnell College, and how we can reproduce it, and how we can make it into great catalysts. Next slide. There's my group. That's the summer SolarArmy Brigade, working on trying to figure out exactly what Stephanie came up with at Grinnell. So over the summer, we not only reproduced it, we made 4 versions of it, even better versions. And then we discovered that you put in little bismuth. You put in little bismuth into the air and it gets better. We now have 10 tremendous hits that have started out with high school students and college students all over the world in our SolarArmy sending us messages via the web from their little stations that they do after school that have come in, and our SolarArmy has upgraded those to Class 1 catalysts to split water. We're getting there. And next slide. So I told Bill I would quit at 8:15 or try so that we could have Q&A. Didn't I, Bill?
You did.
I'm a man of my word. Here we are. We got good catalysts for the photocathode, and now we've got several really good candidates from our SolarArmy for the photoanode. And I've given you one example, but we have several more now. This is what our wires look like. This is a silicon ray. This is what they look like. You've seen those, Ray, from Nate's lab. They're wonderful. We can grow those reproducibly, micron size. We can roll up onto solar carpets. We can make solar carpets out of these. We're really moving ahead. Next slide. We have an annual meeting. We get all these kids together every year. Down at Huntington Beach in a big hotel, I invite all these kids from all over the world to come and interact with us once a year at Huntington Beach. Suze, are you in this photo?
No, I didn't make that.
You didn't make, you know the meeting.
Yeah.
You just didn't make it.
Yeah, I don't remember why.
I don't remember why either, but Suze, I thought Suze would be here somewhere. There's my wife, by the way. She hangs out with us all the time. I've inducted her into the SolarArmy. She's a mathematician, but I forgive her for that. And there I am, of course, and all these characters know Sarah. Nate's in there somewhere. Rich Eisenberg, huh?
Looks like Yogi on the left.
Yogi's on the left.
Looks like it.
That is Yogi. That's Yogi right there. You got it. Do you know Yogi?
He worked with Zing.
Yeah, okay, yeah, that's Yogi. He's fantastic.
I got a picture of him in a tree.
That's Yogi. Okay, that's Yogi, everybody. This is my whole SolarArmy gang. We get together once a year. We mix it up. The kids give posters. The high school kids are there giving presentations. The college kids. This is the real deal. This is so much fun, you wouldn't believe it. It's incredible. Now, I want to thank them all, and I want to show the last slide. Let me tell you where we're going in chemistry. This is the century of chemistry. There's no doubt about it. Some people think it's the century of biology. They're wrong. They're wrong. This is the century of chemistry. This is the world's biggest problem. It's a chemistry problem. It's going to be solved by chemists. It's going to be solved by all you young people going in and getting in and muscling up and working on this problem. It's payback time. You see, think about it. We have been taking what nature gave us. We haven't been giving back. All we've been doing is burning oil, gas, and coal and belching carbon dioxide since the beginning of civilization. We have been taking all the good fuel that nature gave us. It's payback time. It's time for us to figure out how to do it ourselves. Not only make fuel, but make everything else. Make polymers from carbon dioxide. Make fertilizer from nitrogen from the air. We're going to make everything from sunlight, seawater, and these simple components. And I predict that by the middle of this century, we will be able in chemistry to say, we have just started payback time. We have just turned the clock. We are no longer taking from nature and belching up stuff into the atmosphere. We are taking the carbon dioxide and making fuel out of it, and the intermediates for polymers, and frankly, everything else. We're going to make everything in a completely renewable way. Things in and things out balance exactly. That's going to happen because chemists who are working on this problem are going to solve it in the next 40 or 50 years, in my opinion. And I'm very glad that you invited me here so I could share this story with you. Thank you very much. Now we have Q&A, Bill.
We have Q&A.
We got time.
Ask him the question, and I'm going to sit here unless you need me to reference.
All right, we're starting the second row.
Yes.
In the expensive seats.
Cheap seats for the people who can't see well.
Well, I can't see, I can barely see you. I can see Sue's.
You mentioned about the efficiencies of all these other processes, but you haven't mentioned anything about the efficiency of your new cell with these new catalysts that you...
Okay, go back a couple. Let's get to my cell.
There.
Right now we're at the level of, I'm glad you asked that because I can talk about what the next step is. In the NSF program, which we call CCI Solar, I put together, we're working on the pieces, the fundamental pieces. The micro rod silicons with catalysts on them, the micro rod photoanodes with catalysts on them, and the membrane. We can evaluate the efficiency of each piece separately. So what is the hydrogen evolving efficiency of just this silicon piece? We have not put the whole structure together in one unit yet, but I'm going to tell you how that's going to happen. Because we've been working on the individual pieces. You see, in my 17 research groups, each research group has a certain task. At MIT and the Canadian group, it's the membrane. At UC Davis, it's a theory of the silicon surfaces and so forth. At Caltech, it's most of the stuff in MIT, but each of our locations has a certain specific objective in terms of the pieces of this thing. And so we can tell you what the efficiency of the photoanode piece is, if right now the efficiency of the photocathode, but we have not combined the two with the membrane. We have now, I alluded to this, we now have efficiencies that are approaching 10% for the photocathode hydrogen evolution with the cheap catalyst on silicon, and that's equal to what you would have with platinum on it. We have equal to platinum efficiency, which is the highest efficiency you can get. Here we're still around in the 1% area. We've got a lot of work to do, as I said, on the water oxidation, but the catalysts are coming in from the SolarArmy at a rapid rate, and I believe we'll reach high efficiencies in this quite soon from the materials that are coming in. The membrane work is going much more slowly. We have these things and these things, but we have to have a membrane that conducts both protons and electrons at certain key rates. That is a tall order. Paula Hammond is working on it at MIT, and a group headed by Mike Freund is working on it at a university in Canada, in Manitoba. So I can't tell you, but right now our goal is to build an overall device in the next 2 years that will be about, the starting one will be about 2% overall efficient, which is already twice as natural photosynthesis. And then after 5 years or so, something that's 5–6% and so forth. And so we're going to iterate it up. And the plan is, because the solar hub has been awarded to California, the DOE solar hub is the next step. The DOE has granted us $122 million to build, to put these things together into real devices now. And the solar hub, that's a consortium of Caltech, Stanford, and the University of California at Berkeley, University of California at Santa Barbara, University of California at Irvine, and University of California at San Diego. So there's now a big consortium that's starting. It's called JCAP, the Joint Center for Artificial Photosynthesis, just funded by the DOE from Steve Chu for $122 million, which we competed for worldwide. or nationwide with everybody else. But the fact that we had a lot of the components already built and we had a plan helped us get this award of the $122 million for the solar hub. It's going to be like a little Bell Labs. We're going to have a building at Caltech and a building at UC Berkeley, and those buildings, called the North and South Hub, we're going to build these devices. Our goal is to build one with reasonable efficiency within 2 years that we can actually take to Washington and show to Congress. So that's where we stand. I can give you the individual efficiencies as I have. The overall efficiency I'll be able to tell you in 2 years. Others? Yes? Anna, you're going to ask me again. You're my very favorite questioner.
I actually have 2 questions.
You have 2 questions. Well, since you're a brilliant student, I will allow you 3.
I think that some reactions that are catalyzed by platinum are often also catalyzed by vanadium pentoxide. Why doesn't it work?
Well, I'm not sure. Yeah, what Anna, who's a student here, I believe a sophomore, if I remember right. I had lots of talks with Anna today. She's a very bright gal who's a sophomore here. She has just told me that there are a lot of reactions that are catalyzed by platinum that are also catalyzed by vanadium oxide. Now, the problem, Anna, is these reactions are the ones that I'm not interested in. Like the oxidation of methane on vanadium, for example. You can do methane to methanol, for example, on vanadium. But I don't want to oxidize methane. I want to make methane out of carbon dioxide. I want to go the other direction. So the oxidation reactions, which many people are interested in, including the Burkhardt group, are the opposite of what I'm trying to do, which is to make the fuels to begin with. It's to make the energy-rich materials to begin with. The ones you're talking about, vanadium, are taking energy-rich molecules like hydrocarbons and then converting them to alcohols and other high value-added products. And so vanadium does not catalyze the reactions I am interested in. And what's the second question? Are you satisfied with that answer?
Yeah.
Yep. That's what's nice about Anna. Practically anything I say, she's satisfied with. I could be kidding her, but in this case, I'm not. What's the second one?
How can a student join the SolarArmy?
You could have all during the day I said Richmond would be a great place to have a SolarArmy brigade. I've seen your undergraduates, and I know you have some connections now to high schools. And I'm particularly interested in undergraduate schools that will connect to high school through mentors like Sue's did at Caltech, at Polytechnic School. And so if you guys are interested, Anna, in joining the SolarArmy, and by the way, I have only 2 ranks, private and 5-star general. Brad, we got uniforms. We got uniforms. I got these cheap T-shirts for privates, and I got a really slick-looking 5-star general with your name on it. It's real cool. You see, Suze, you've seen that. You have a 5-star general, don't you, Suze?
No, I said the regular T-shirt.
Oh, I got to get you a 5-star general. So, you go on the CCI Solar website. You go to Outreach. You go to the SolarArmy. Our field commander is a gal by the name of Jenny Shuttlefield. She's at the University of Wisconsin, Oshkosh. Her email is there. You email Jenny Shuttlefield at the University of Wisconsin, Oshkosh, and say, I want to join the I want to have a brigade at Richmond in the SolarArmy, and you shall have one. We'll make it happen. If you want to get involved, and if you want to be a loner here, we'll move you to one of the locations where we have a SolarArmy. Listen, we can move her to Grinnell, to Reed. We want to go to Germany, we'll send you there. You want to go back to Romania? We'll start a SolarArmy in Romania. If you want to have one here, maybe, how about Charlottesville? Suze?
We can do it here.
I think this would be a good location because I've heard you guys have connections with outreach to high schools. And that's really what we're looking for. We're looking to get really young kids into this early on and getting an after-school activity and interacting with kids in colleges so there's mentor relationships all the way. And so if you guys are interested, I would love to have you in the SolarArmy. I will order new general shirts immediately. I will get one with your name on it, Anna, a 5-star general shirt. And so go on the website and email Jenny Shuttlefield at the University of Wisconsin, Oshkosh. Okay, that's the way to do it. Right, Suze? And then Jenny will, we've got a big operation. Jenny will get to you and we'll get you in line. By the way, we have a whole new sampling technique. The old one was, and Suze will verify this, the old one's very slow. We have this way of sampling with the inkjet printers. Well, the inkjet printers clog. No matter what you do, they clog and there's problems. So now we've got a pipette sampling technique, different sampling techniques on an 8x8 plate. And we got a pulsar now. You haven't seen these, Suze, but we've got these pulsars now, 8x8 pulsars that have little LEDs, different colored LEDs that we get at Home Depot. We can buy these LEDs at Home Depot for 20 cents each. We got an 8x8 array and they blink like this and they look cool, blinking lights, and we plaster these onto our materials, and just in a few minutes with a monitor you can see your catalyst activity going up and up. It's cool. So we could set you up with the new beta test that we're doing with the LEDs and the other stuff. And so email Jenny, okay? Or you better talk to somebody over here. You better talk to Ray. You better check with Ray, because if you do something without Ray agreeing, you'll probably be in deep trouble. But Ray looks like he's going to buy into this. Yes?
Is there any concern about patents with all this work?
Well, every one of these is a new composition of matter. We could patent every single new composition of matter. We don't know what to do. I feel like Madame Curie, who could have patented radium, but she wanted it available to the community. I feel that way about these materials. Although we have you can imagine the complex intellectual property arrangements we have with all these different sites and stuff. And if we really find the material that's going to replace platinum in catalytic converters in automobiles, for example, or in fuel cells, but especially in automobiles. If we can replace platinum in automobiles, this is a huge market. We're talking billions of dollars. And so intellectual property is an interesting issue, which we have arrangements through the NSF and DOE and stuff, and we've wrestled with it at each site and so forth and tried to solve them separately. But we don't have a really great way to deal with it at the moment. We've worked hard on it. Back in the back.
I just have a question. Do you help fund some of the schools you want to work with in the area?
Do we fund?
Yeah, do you help?
Yeah, we fund it. Thus far, we have funded every school that, I think that's true, isn't it, Suze? I think we have funded in terms of getting the equipment in, our setup. You see, we train, we have mentorships, we have workshops. Suze has been involved in them. She could tell you more about it, but we get teachers in, and we get teachers to assemble the stuff, the Lego stuff, and work with the inkjet printers. We just don't throw it out there. We have workshops, we have training systems. So the people who join our SolarArmy, Jenny Shuttlefield, we would come out here. We would come out here and work with people. If we did it here, we'd come out here. There'd be a group to work with it and make sure the setup works and so forth. And thus far, we have funded all of the solar discovery kits that we put in schools. We have funded from our grant. we're getting to the point, we're getting so many now, we're overwhelmed, and we have to have some financial model that can take us into the future, because frankly, I want thousands of kids. I want thousands and thousands of kids to join the SolarArmy. I think it's a wonderful recruiting tool for scientists, for kids. And I hate to say this because I know there are a bunch of lawyers in the audience, but one of my goals is to keep these kids from becoming lawyers. I apologize for all the attorneys in the audience, but our college presidents, lawyers, they're okay. It's okay if they're medical doctors. I'm willing to go with that. Yes?
I understand from what you say that mainly you're looking at mixed metal oxides, and the question is, are there any other more exotic ligands that you're looking at?
No. No, we're not looking at anything but mixed metal oxides. Our very strong feeling is that ligands are going to be decomposed in these very high oxidation systems, and they're going to oxidize away in this environment. And the only thing that will really do the water oxidation is a metal oxide. This is our hypothesis. So we're not looking at any ligands at all. We're only looking at mixed metals and oxides. For the hydrogen side, we're looking at ligands because that's a reductive side, and they will stand up with ligands. They'll stand up to electrons at low potentials, but at high potentials, ligands will oxidize away. There's no ligands that won't oxidize away that we know of. So on the reductive side, we're using ligands and catalysts. On the oxidized side, it's just mixed metal oxides. There's one more back there. There's somebody holding up a hand back there. Shout it out. Shout out your question.
Okay. But just a really quick question. I'm sorry.
You mean you have a really good question?
No, a really quick question.
Oh, a really quick question.
Okay.
But is it good? I'm sure it is. Go ahead. I'm sorry.
Just from what I can understand about the process of what this seems like kind of a random search.
It's a random search. Yeah, we have no idea what we're looking for.
Okay.
We're out there.
Well, that's what I was
We don't care. Chemists think that they understand mechanisms and they can make something. Wrong. You got to be out there searching, man. You got to look at a lot of things and find something good.
So as a result,
All chemists know that.
okay. So if it's just a really kind of a random, pick this stuff, search through the elements, is there very specific advantages to using groups of people as opposed to just kind of getting?
Yeah, I think it's a great thing with groups of people. They interact, they talk about things they're going to do. Our little groups of 4 or 5 people have made a big difference, I think, not in isolation, but kids working together, talking about ideas. The bismuth thing came about a group actually saying, why don't we try bismuth? You know, if you go back to my thing, Lisa, you'll see that bismuth is not in my search algorithm. You go back. Keep going, keep going, keep going. There. You see, bismuth's out here. I told them to search in here. They ignored me. The kids do what they want. The kids in the little group of 4 said, let's have a look at bismuth. Bismuth oxide is yellow. If you put a little bismuth oxide and a little iron oxide together, you get a deeply colored stuff that's a fantastic water oxidation catalyst. And the amount of bismuth you put in is in a very short range of bismuth concentration. A little bit too much, it doesn't work. Not enough, it doesn't work. It's got to be just right. This group of 5 kids figured that out. 5 kids figured that out and got it to us. They worked outside. There's a lot of good stuff out here, aluminum and stuff. They say, Harry, why don't we? So they ignored me. They're out here working. And so kids will, I've got great faith in kids who are just searching around and looking at things and talking to each other. I think the groups of people talking with their mentors, it's a great thing. I really believe in it, and I believe in this. By the way, I'll throw a bone to the theoreticians in the audience. Kelling's up there sort of scowling at me because I just said, theories basically in this field is useless because nobody knows what we're looking for. The fact is, theory is super important because once we get zeroed in on one of these great catalysts, we have got to figure out why it's working. we have really got to zero in and find out what is the structure around the iron that makes this so much better than just regular iron oxide. What is it about the electronic structure? And what about the surface and stuff? There's a huge role, you see, after the kids discover this, it's a huge role for theory, for really strong, X-ray diffraction, all sorts of synchrotron stuff, all kinds of physical techniques to really figure out what we've got. So that's where the real action starts, Kelly, and where we're going to desperately, we got theoreticians in our operation working on this. So once the materials are discovered, we got to figure out why they're so good. So we can work in that part of the periodic table. We can work over, we can reduce the search down to some of the elements we know are really working great. And right now we know that iron oxide, plain old iron rust, doped with a few things like bismuth and yttrium and a few things like that, becomes really a good catalyst. And we got to figure out why. And that's going to involve a huge research effort. So these kids are generating a whole, enormous array of great research problems for chemistry right now. And so I wanted to tell you that, Kelly. We're going to need you, Kelly. We're going to need, in the long run, we're going to need you, man. So just stay in there, okay? Stay in there. Don't listen to me about all this stuff. Stick with me, because if Anna starts a SolarArmy here, you're in, baby. You're in. We got, okay, way back up in the corner. We got a great crowd, Bill. I told you we get good Q&A. It's already 8:45. And we've had 30 minutes of Q&A. Anna, did you have another question? No. Where are we? Way up there. So far I can't see. Shout it out.
I was just going to ask, did you try, since bismuth and yttrium work so well, did you try the other elements in those groups with similar chemistry?
I don't try anything the kids do. I don't think they've tried some of these things. Suze, do you know?
Yeah, we were not working with scandium.
You weren't working over here. Where were you guys working?
We were most iron, cobalt, nickel.
Iron, cobalt, and nickel in here.
We tried aluminum too, but that.
Oh, you tried aluminum. You also ignored what I said.
Yeah.
You're out of the box too. Okay, yeah, see, there you go. I have no idea. Kids are out there doing their own thing. They're making little groups. They're discussing it. I don't give any orders. I'm a general that doesn't give orders. We need more generals who don't give orders. The kids are discovering. I can't tell you where they're working right now. I only see them when the hits come in. I see them when the hits come in. And a bunch of hits have come in with yttrium, but nothing with scandium. So that's the best I can answer your question. But that would be logical. It would be logical to look at some of the rare earths. It'd be fun to look at some of these funny elements down there in the rare earths and so on. But that's where we are. You had one more.
Yes. In light of what's going on in Japan.
Oh yes, that's it's a super tragedy.
And what's going on in Washington in terms of cutting the budget, the discretionary spending, your funding is not guaranteed.
No, it's not. It may be cut off. It
Right.
may well be because of what's going on in Washington now. This $122 million to do our next step may actually be taken back. That's a very real possibility.
Right. Have you explored other sources of funding?
Yes, we have. Private funding.
What's happening in Japan may give more emphasis to alternatives.
Yeah, well, I certainly, I'm not anti-nuclear. Let me make that clear. This is not an effort to try to knock anyone else out. And my own feeling, my very strong feeling is that we need all the nuclear and all the wind power that we can bring to bear on this problem. So I see the future as a mix in energy, a mix of nuclear, wind, and solar. The tragedy in Japan is definitely going to set back nuclear. Commissioning new nuclear plants is going to be more and more difficult. I think that's tragic, and I think the tragedy for the Japanese people goes without saying. The situation in Washington and the money, we may well lose half this funding. because the DOE and you know what's going on in Washington now, we're big in debt. But we will keep going. We will keep going because I have a plan that working with kids that I can keep going without all that much money. It will set back building real devices out of the fundamental work we are doing, but I guarantee you the fundamental work will continue to go on. We have a lot of potential private supporters. There's a very rich man in Southern California whose name is Donald Bren. And there are other rich people like Gordon Moore, who founded Intel. These are all Caltech people. They're all extremely rich, and they're all extremely supportive. And so we believe we can go to Donald Bren and Gordon Moore and the Beckman Foundation if necessary, but the real heavy hitters are Gordon Moore and Donald Bren. And they're both very interested in what we're doing and have already supported it privately to a great degree. A lot of the Moore grant, which we call Caesar, Suze, you know about it on campus, a lot of them, Gordon Moore gave us $600 million to Caltech for various things. Part of it, not all of it we've used for them, but part of it is used to develop our solar capability. So we have private resources which we will go to. We will go to anyway because it's much easier to work with private money than it is with government money. And so we're very optimistic we can make it through this particular crisis with help from very loyal supporters of Caltech who have supported us for years, and we believe are going to support us because there are a lot of people in the world now who understand this problem that we're facing on this planet. And if we do not solve this problem, it won't be the next century because we won't be here. We have to solve this problem in this century. We have to solve this problem before 2050. We all know that. And a lot of very wealthy people know that and are very supportive. And so if the DOE bails on us, Suze, which they don't want to, but they may have to because of the climate now and the fact that we're $10 trillion in debt. I mean, at some point we've got to do something. So I understand all this. The government has been very good in supporting us up to now. It's up to us to keep fighting and raising the money and making the case. And I'm very optimistic we will carry on.
I have a hypothetical suggestion.
Yes.
University of Richmond, I believe, is kind of in Eric Cantor's congressional district. Is that not true? 7th district. Yeah.
You have a congressman we can talk to?
Well, he's kind of high up, and
that's good.
so it'd be nice if he was invited, and then he could get to talk.
Yeah, he should be here tonight. I could talk to him. I
You
could.
don't get to go to Washington. and talk
Well,
to
we
Congress.
talked to a lot of Congress people, and you know Nate Lewis and a lot of people in our program have been very active in raising the flag in Washington.
If
We
you get the SolarArmy at University of Richmond, then you got a tie. See? That's
yeah.
something.
Well, I would be very happy to have a brigade here. I'd be very proud of a brigade here. And the brigade, then we can do a march on Washington. Suze and I will lead the charge. We'll be out front with big generals singing. We'll have a sit-in on the Capitol. No, we're going to solve this. Don't worry.